Assalamu alaikum. Assalamu alaikum everyone. Dear students, welcome. I wanna make a summarize. I will summarize here the most important definition, theorems, and results about extremum. First, let subset A be included in R or part of R. We say that A is upper bounded. We say that A is upper bounded if there exists a real number m such that for all x in A, x is less than or equal to m. By symmetry, we say that A is lower bounded, if there exists a real number m such that for all x in A, x is greater than or equal to m. And subset of R is said to be bounded, just bounded, if it is at the same time upper bounded and lower bounded. This is the most important definition about extremum. Second point, we have completeness theorem, completeness axiom. Completeness axiom says that for any upper bounded subset of R admits a supremum. The supremum, by definition, is the least upper bound, and the supremum is the least, the smallest, the least upper bound, the smallest one. As a corollary of this axiom, we can show that and if A is lower bounded, then A admits an infimum. So our lower bounded set admits an infimum. And if it is the infimum is actually the greatest lower bound, which is the greatest, the bigger, the greatest lower bound. This is the most important definitions, axiom, and corollary. Notation. If I is bounded, then we denote by sub A, the supremum, of A, and Fa, the infimum of A. We have maximum and minimum. I will talk about them later. Don't forget, this is just a summary of what we should know about this chapter or this topic. If we have two parts, subset of R, and if we suppose that A and B are bounded, A, B bounded, then we have the sup of A union B. This is equal to the maximum, we prove this, of sup A sup B, and the minimum, the infimum of A union B. This is equal to the minimum of nth A and B, and the sup of A plus B, which is the set A plus B is defined by x plus y such that x belongs to A and y belongs to B. This is equal to sup A plus sup B, and the infimum of is equal to the infimum of A plus the infimum of B. These results are very, very useful while solving some exercise, and I will use these formulas to prove something about these two sets while discussing some exercise, I mean examples. The last important theorem is about characterization. So sometimes we can use characterization to prove the existence of the supremum. We can also use it to prove for infimum, minimum, and maximum. For minimum and maximum, it is very easy. For this reason, we don't need to use characterization. Characterization of the supremum, so characterization of sup and nth of a set. Theorem. we have the characterization m equal to capital M equal the sup of the bounded and upper bounded set I. This is equivalent to verify the following. One, for all x belonging to I, x is less than or equal M. And the second condition, for all epsilon greater than 0, there exists x epsilon which belongs to I and which verifies m minus epsilon strictly less than x epsilon less than or equal capital F. We can read this information here. This information, we can read it as follows. If we move just epsilon, m minus epsilon doesn't steal an upper bound. This is what we can understand from this. And about the infimum is equal to infimum A. This is equivalent. We suppose that A is lower bounded. In this case, we have equivalence between these two properties and this information here. For all x in A, x is greater than or equal little m, and for all epsilon greater than 0, there exists x epsilon from A such that little m less than or equal to x epsilon, which is strictly less than little m plus epsilon. And this information here means that if we move just a little, m plus epsilon doesn't steal an lower bound. We usually use this characterization to prove about supremum and infimum. This is the most important definitions and theorems that we can meet while studying or solving exercises about extremum. This is just a reminder for someone who studied seriously this chapter. This to just make him more prudent about informations in this chapter. For A, this was an exercise in National High School of Mathematics, I think 23 plus n over 2n plus 1, n belongs to n 0. This means index 0, this means 0 is included. We have a couple union 2 minus 1 over n plus 1, and n belongs to n index 0. So we have all the right by definition. A can be transformed into the union of two parts. We will call this one A1 and this A2. From what we can solve just one of A1 or A2. For the first one, for example, A1, we can keep it as it is, but we can transform it 1/2 plus 1/2 times 2n over 2n plus 1 So we divide 2 by 2, we get our function. We add 1 and we take out minus 1. This is our A1. And here we get 1/2 plus the first 1/2, first this one, minus 1/2 times 2n plus 1. And n belongs to n0. This just to let n in one place. And 1/2 plus 1/2 gives us 1. We are dealing about the supremum, the infimum of A1. We have at least three different ways to answer this question. I will use the most classical way and not the shortest one and the beautiful one. I will just use the customary methods to solve this exercise, and believe me, there is other methods, very nice methods. I can tell you that you can use the sequential characterization of supremum and infimum, since this set is defined just by sequences. Try to see if it is increasing or decreasing, and you have a very nice results and very quickly results. Let us study this one. We have n in n0. This means that n is greater than or equal to 0. This implies that for n is greater than or equal to 0, which is equivalent with 4n plus 2 is greater than or equal to 2. If we take the inverse, this will gives us 1/4n plus 2. This is less than or equal 1/2, and this is equivalent with minus 1/4n plus 2 greater than or equal to minus 1/2. Then we add 1, and this is equivalent to say that 1 minus 1/4n plus 2, this is greater than or equal to minus 1/2 plus 1/2 from this side. And from this side, this is greater than or equal. We are here. If we divide, this is strictly greater than 0 from this side, because we have the positive terms. Which means that here we have greater and less than 0. If we add, we get here, if we add 1 to each inequality, we get here strictly less than 1. This results allows us to say that for any element x from A1, element x is less than 1 and greater than or equal to 1/2. This means that A1 is bounded above and lower. I will just do a solution detailed solution just for A1, and we do the same with A2. A1 is equal to 1 minus 1 over 4n plus 2, and belongs to n 0. And for any given element of A1, this element is included between 1 and 1/2. The greatest lower bound is 1 over 2 for n equals 0. For n equals 0, we have x0 is equal to 1 over 2, which belongs to A1. So since it belongs, this implies that the infimum of A1 is equal to the minimum of A1 and is equal to 1/2. We haven't here, we don't need here to use characterization, since the element 1/2 belongs to A1 and is the greatest lower bound of this set. We expect that 1 will be the sup, and we need to show that using characterization. Let us show that the sup of A1 is equal to 1. We have the first condition for all xn from A1. We have xn. Xn is this element. This is xn. Xn is less than or equal 1. Actually, is strictly less than 1, but it doesn't matter if we write less than or equal. The second information, when n goes to we get is less than or equal to 1. The second condition, for all epsilon greater than 0, can we find xn 0 from A1 such that what? Such that 1 minus epsilon is strictly less xn 0, which is less than or equal 1. So the first one is verified from what we did before. Let us just find, we take epsilon any given real number, and let us try to find an element from A1 which verifies this double inequality, in this sense, less than or equal and strictly greater than. Here, the form of any element of A1 take this form. So what we can write this one is this one can take this form. So 1 minus epsilon, can we find n0 such that 1 minus epsilon is less than 1 minus 1 over 4n plus 2. From here, what we can find, we can this is equivalent to say that minus epsilon is less than minus 1 over 4n plus 2. And this is equivalent to say that epsilon is greater than 1 over 4n plus 2, which is equivalent to say that 4n plus 2 is greater than 1 over epsilon, which is equivalent to say that 4n greater than 1 over epsilon minus 2, which is equivalent to say that n is greater than 1 over 4 times 1 over epsilon minus 2, and we have, this is a very strict estimation, but we can simplify more than this one. So we are here. Can we find for any given epsilon, can we find a natural number and such that this number is greater than 1? And here we have cases. If epsilon, for example, is between more than 1/2, if epsilon is greater than 1/2, here we get something which is positive, which is negative. 1 over 1 over 2, we get 2 minus 2, this is equal to 0. If we take, for example, 1 over 3, 1 over 4, 1 over 4, less than, I will do it properly. One over epsilon minus 2 negative. 1 over epsilon minus 2 negative. This means 1 over epsilon less than 2. This means that epsilon should be greater than 1/2. So if epsilon is strictly greater than 1/2, here we get something which is negative. Let me show that epsilon greater than 1/2. Yeah, 1 over epsilon minus 2 less than 0. 1 over epsilon less than 2. So epsilon greater than 1/2. Yeah, if we get epsilon greater than 1/2, we get this is a negative, and any natural number starting from 1 verifies this inequality. So this case is trivial. For epsilon, which is less than 1/2 and greater than 0, for this case we can take the natural number and 0, the integer part of 1 over 4, 1 over epsilon minus 2 plus 1, for example, or we can say this is true. Why? Because the Archimedean property of R, which say that for any real number we can find a natural number which is greater than this number, and this allows us to say that the supremum of A1 is equal to 1. To find the supremum of A, we found the supremum of A1, we find the supremum of A2, and then, since it is union, the supremum of A is equal to the supremum of the maximum between the supremum of the first and the supremum of the second, and about the minimum, we take the minimum between the infimum of the first and the infimum of the second. This is a way. I cannot detail more, makes more details, to let the video be not very long. For B, very smart idea. For B, we can B, which is n plus 2 n over n plus n plus n plus 1. We can write it n over n plus 1 plus n over n plus 1 and n in n 0. This is equal to n over n plus 1 n in n index 0 plus n over n plus 1 and n in n index 0. This is equal to the same we have here. We call this A, and this is B, A plus B. So B1, B2, B1, B2, N and M belongs to the same set. So we are adding M is any given natural number and M is any given natural number. So the supremum of B1 and the supremum of B2, actually here we have the same thing, B1 plus B1, which is equal to 2, B1. This kind of thinking just about the supremum and the infimum, not about the set itself. Not about the set itself. So we take this one, B1 plus B2, and about the sup of B, the sup of B is equal to the sup of B1 plus B2. And this is equal to the sup of B1 plus the sup of B2. And the infimum of B is the infimum of B1 plus B2. And this is equal to the infimum of B1 plus the infimum of B. So what we can do, since the supremum of B1 and B2 are the same, since they are the same form, we can just calculate 1 and times the one that we found, we will times it by 2. Same thing with the infimum. Search the supremum of and infimum of n over n plus 1 is easy. We add 1 with times minus 1 and we can use the characterization for the maximum, the supremum, and for the minimum it is equal to 0 for both, and for the supremum is equal to 1. So for B we have here, we have the minimum B equal infimum B and equal 0, and the supremum of B is equal to actually is equal to 2. We can use characterization for one of the symmetric or similar subsets B1 or B2. They define the same sets. I think that this video was a little bit long. Thank you very much for watching. I tried my best to give you a summarize about this chapter. Thank you very much for watching. See you next time.